So this, we can say, this is the overtaking vehicle. This is the overtaking vehicle, and this is the slowly moving vehicle. Slowly moving vehicle. So you can see it's a two-way road. Okay, two-way road, and here it is the overtaking operation. Okay. Hello everyone, welcome you all to Edu Portal. So how are you all? I hope you all are doing great. So in this video series, we are going to solve questions for SSC JEE mains for civil engineering. And as you know, in the mains examination, that is in the paper number 2, it's a conventional type paper. And to crack this examination, you need to practice these conventional type questions uh, to revise your concept, to increase your speed and accuracy, and for better time management. Okay, and the best thing available for doing this is the previous year's questions. Okay, so in this video series, in each video we will solve previous year's conventional type questions for SSC JEE mains, and we will solve the questions in detail with full explanation, and it will include theoretical and numerical questions as well. Okay, so let's see today's question and let's solve it step by step. So let's get started. Okay, so here is the question for you, and it is from the SSC mains examination that was conducted in the year 2019. So it's a question from SSC mains examination that was conducted in the year 2019. So this is this is question number 1, and it has 4 parts. Question 1A, 1B, 1C, and 1D. And each question is for 15 marks. So total for question number 1, 60 marks has been allotted. Okay, so 60 marks. Okay, so let's solve the first question number 1A. So it says, for a town with population 2 lakhs, a water supply scheme has to be designed. The maximum daily demand is 200 liter per capita per day. The storage reservoir is situated 5 kilometer away from the town. And assuming the loss of heads, that means the head loss from the source to the town is 10 meter, and the coefficient of friction for the pipe material is 0.012. Then recommend the size of the supply main. That means what should be the internal diameter of the supply pipe. Okay, for 50% of the daily demand has to be pumped in 8 hours for the proposed scheme. Okay, so let's solve the question, and here we need to determine the size of the pipe main, that is the internal diameter of the main pipe. So let's solve it. So here is the question in short. First, population 2 into 10 to the power 5, that means 2 lakh. Q max, that is maximum daily demand, it's 200 liter per capita per day. The distance from the reservoir to the town is 5 kilometer, that means 5000 meter. And HF is the head loss, that is head loss due to friction, it is 10 meter. And F dash is the coefficient of friction, 0.012. And be careful, it's given coefficient of friction, not the friction factor. Okay, so that we will discuss later. And the supply is 50% of daily demand at the rate 8-hour pumping per day. This is important. So not 24 hours, not 24 hours. Okay, so most students make a mistake here, not 24 hours of pumping. So it should be 8 hours pumping. Okay, now let's move to the solution. So this first step number 1. Step number 1. Q is the discharge. Q is the discharge in meter cube per second. So first of all, 200 liter, that means we know 1 liter is equal to 10 to the power minus 3 meter cube. Okay, so 10 to the power minus 3 meter cube, that's why we have multiplied 10 to the power minus 3. So this is in meter cube. Now it's given LPCD, liter per capita per day. Now total population is 2 lakh, that so we multiplied 2 into 10 to the power 5 here. So this is the population. This is a population, and 50%. That means we 50% of the maximum daily demand has to be supplied at the rate 8 hours per day. Okay, so 8 hours mean 8 into 3600 second. Okay, so that's why, so this is meter cube, this is population, and this is second. Okay, so we get q as the discharge equal to 0.06944 meter cube per second. This is number one. Okay, so we get this. Now step number two. So as we get discharge, now what we should determine? So given the head loss due to friction, head loss due to friction, head loss due to FL V square by 2 GD, and sometimes we see this equation as HF is equal to 4F dash L V square by 2 GD. What is the difference? Okay, both the same equation. It is known as Darcy-Weisbach equation for pipe flow. Now what is the difference? See, the difference is here, F and 4F dash. Okay, now this is the mistake that most of the students do while solving this question. It's given that friction is given that coefficient of friction is 0.012. F dash is the coefficient of friction. Okay, what is the relation between friction factor and coefficient of friction? Friction factor is F. F is equal to 4F dash. So friction factor is equal to 4 multiplied by coefficient of friction. Okay, so when we are using, so this is the friction factor. This is friction factor, and here F dash is the coefficient of friction. Friction. In the question, it is given that coefficient of friction, that is F dash, it is 0.012. So we have to use 4F dash. Okay, because it is coefficient of friction, so we have to use 4F dash, because 4F dash is the equal to F, equal to the friction factor. Okay, now L you know as the distance between reservoir and town, and its value is 5 kilometer, that is 5000 meter. And 4F dash is coefficient of friction, that is 0.012. And now FLV square, we know V equal to velocity of flow is equal to Q by A. Q is the discharge and A is the area of cross section. Okay, so that's why we have written Q by A whole square. Now V is the velocity of flow. Now what is A? Pi by 4 into D square, where D is the internal diameter of the pipe. Okay, so A is the pi by 4 into D square. So if we put it here, we get Q, the value of Q we have determined 6944. This is meter cube per, this is a meter cube per second, that is value of Q, and this is in meter, this is L length, and this is F dash coefficient of friction. And 2G to 9.81 into D, we don't know the value of D, so here A square, that means pi by 4 whole square into D square, that means pi by 4 whole square into D to the power 4. Okay, so here D to the power 4, and here 1 D is here, so that's why it is pi by 4 whole square into D to the power 5. Okay, so from here, if we take D here, D to the power 5 here, and 10 here, so we determine D is equal to something to the power 1 by 5. Okay, so this is the D. So okay, so we have determined the value of D. Thus using calculator we can solve it, and we get the value of D equal to 0.99 meter, or almost 1 meter. Okay, so when we are going to design something, we need to put a value that is realistic. So value of the internal diameter of the main pipe, this is DI, that is the internal dia of main pipe. Okay, so size of the supply main, that is size is the internal diameter, and the diameter of the pipe is 1 meter. Okay, so this is the solution of the question. So the question has been asked as recommend the recommend the size of main. So this is the size of main, that is the internal diameter of the main pipe should be 1 meter. Okay, so we have solved the question number 1. Okay, now let's move to the second question. Now question number 2. Okay, so we have solved the question number 1. Now question number 2, not 2, it is second part, that means 1b. So it says a certain clay layer of thickness 5 meter. After 1 year, when the clay was 50% consolidated, that means the degree of consolidation after 1 year is 50% and 8 centimeter settlement has occurred. For a similar clay, that means the soil type is same, loading and condition. So in both cases, the soil type and loading conditions are same. How much settlement would occur at the end of 1 year and 4 years respectively if the thickness of the new layer is 25 meter? So this is the question. Now we will solve this question. So we have first the soil sample 1. Okay, so for the soil sample 1, the thickness of the soil is given as 5 meter. T1 is 1 year, that is after 1 year, degree of consolidation, U1 is a degree of consolidation for sample number 1. It is 50% after 1 year. This is percentage of consolidation or degree of consolidation. Del H1 is 8 centimeter. Del H1 is the settlement. Settlement is 8 centimeter, that means 0.08 meter. Let's take del H1U. So it is the ultimate settlement of the soil layer. Okay. Now we know from the definition of degree of consolidation equal to settlement. So degree of consolidation UT, that means at time t, that is so del H T, that means settlement at any time t by del H U, that means the ultimate settlement. Okay, so we have taken like this. So del H1, that is settlement of the sample 1 by del H1 U, that is ultimate settlement of the sample 1 into 100% is the U1, that is the percentage of consolidation. Okay, so doing this we get, so del H1 by del H1U is 0.5, that is given as 50% consolidation after 1 year. Okay, so 50%, that means 0.5. Now del H1 is given as 8 centimeters, so 8 by del H1U is equal to 0.5. So here we get del H1U, that is the ultimate settlement. So this is the ultimate settlement for sample 1. Okay, it is we have found this as 16 centimeter. Okay, so we need to keep this value because it will help to determine other values as well. So now step number 2. So we have got this. Step number 2, for U less than 60%, we know for degree of consolidation less than equal to 60%, less than equal to 60%, we have TV. TV is known as the time factor. TV is the time factor. Okay, time factor. So value of TV will be equal to pi by 4 into U percentage by 100 square. That means if we write U in percentage, we need to divide it by 100. So TV is equal to pi by 4 by 50 by 100 square, because we have for soil sample 1 we have degree of consolidation as 50%. So that's why we have written 50 by 100 square. So doing this we get TV, that is time factor for U 50%, that is for 50% consolidation the time factor is 0.196. okay, this is important. Now next step, that is step number 3. So the type of drainage is not given, so let's assume single drainage. Okay, so if for all same conditions, if For sample 1 we take single drainage, for sample 2 we will have to take single drainage. Okay, so this is same for sample 1 and sample 2. Okay, now TV is the time factor is equal to CV, that is coefficient of consolidation, into T by H square. T is the time and H is the length of drainage path. Okay, that we generally indicate by D, but because it is single drainage, so in that case D is equal to H, that is the thickness of the layer. Okay, so now we know the value, we don't know the value of CV, but we know T is equal to 1 year, that is after 1 year, and H is the thickness of the layer, that is 5 meters. Okay, and T is the TV for 50% consolidation, at the value of TV is 0.196, that we have determined. So if we put these values here, we get the value of CV equal to 4.9 meter square per year. Okay, so this is same for both soil, because both soil type are same, so it depends upon the soil type. So it will be same for both the soils. Okay, so this value we need to use again. So CV is equal to 4.9 meter square per year. Now next, now we will take the soil sample number 2. So here it is step number 4. So H2 is the thickness of the soil it equal to 25 meter. So we had taken thick H1, that is thickness of the soil sample 1 is equal to 5 meter. Here H2 equal to thickness of the soil sample 2, 25 meter. We know that for a particular type of soil, so this is very important, for a particular type of soil, H1 by H2 is equal to del H1U by del H1 2U. That is the ratio for the same type of soil, the ratio of the height of soil layer is equal to the ratio of their ultimate settlement. Okay, the ratio of their ultimate settlement. So because we know the equation del H is equal to, we know the value of del H, that is proportional to H. Okay, so that's why del H1 by del H2 equal to H1 by H2. Okay, so that's why this should be used. So ratio of ultimate settlement will be same. Now 5 by 25. So because of same type of loading, so what are the conditions for this equation to be valid? Same loading. Okay, same loading and same soil. So if the loading condition is same, drainage condition is same, and same type of soil is there, so this condition is valid. So here we know the thickness of the sample number 1 is 5 meter, thickness of the sample number 2 is 25 meter, and the del H1U that we have determined equal to 0.16, and del H2U, that is ultimate settlement. So del H2U is the ultimate settlement for soil sample 2. It has been, from this equation it has been found del H2U equal to 0.8 meter, that is 80 centimeter. Okay, so del H soil for soil sample 1, del H1U, it is 16 centimeter, that is ultimate settlement for soil sample 1 is 16 centimeter, and del H2U ultimate settlement for soil sample 2 is 80 centimeter. Okay, so these two values we have found. Now step number 5. So for that second type of soil, when TA equal to 1 year, when time equal to 1 year. Okay, so again we will use this equation. So TVA. Okay, so for 60 percentage of for, we assume that degree of consolidation is less than 60%, less than equal to 60%. So TVA equal to pi by 4 by UA square. That this equation can be used. So using this equation, CV value we know 4.9, and TA equal to 1 year, H2 is equal to 25. So from here, using all these values, we get the degree of consolidation after 1 year for soil sample 2 is 10%. Degree of consolidation. Degree of consolidation. So degree of consolidation. So for soil sample 2, after 1 year, the degree of consolidation is 10%. Now, step number 6. Degree of consolidation 10%, ultimate settlement 80 centimeter. Okay, so after 1 year, what should be the settlement? Again, we use that equation. So del HA, that is, this is the settlement of the soil layer after 1 year. This is ultimate settlement, and we know the degree of settlement. So from here, del HA, that is the settlement after 1 year. Okay, 1 year. From here, if we put these values, we get del h1 is equal to 8 centimeter. Okay, so settlement of the soil sample 2 after 1 year is 8 centimeter. Okay, so this is solution. Okay, now the same thing, yeah, it asked what will be the settlement after 2 years. Okay, so what should be the settlement? So here we have to put these values, and so here, okay, so here we need to put these values. So let's see the question once again. So it said after 4 years, sorry, after 4 years. So if we put these values, soil sample 2 10%. So if we put these values, so this is after 4 years. So TV is equal to 4 years. After 4 years, if we put all these values, now again we assume that degree of consolidation less than 60%. So that's why TV will be pi by 4 into UB square. So UB is the degree of consolidation after 4 years. Okay, so if we put the value of all these values, so CV same will be same because the soil type is same. TB is the 4 year, H2 is equal to 25, and so here we get UB, that is the degree of consolidation, as 20%. So after 4 year, the degree of consolidation is 20%. This is after 4 years. After 4 years, the degree of consolidation is 20%. Okay, so again same, del H2U ultimate settlement is 80 centimeter, that we have already found. Then so what will be the degree of consolidation, so what will be the settlement after 4 years? So suppose del HB is the settlement after 4 years. So again putting these values, del H2U we know 80 centimeter, 100, and degree of consolidation 20%. So if we put all these values, we get del HB equal to 16 centimeters. So this is the answer. Okay, so what we have found is that del H A, so this is T is equal to 1 year. So for soil sample 2, this is this we have found as 8 centimeter, 8 centimeter, and del HB, that is for T is equal to 4 years, it is equal to 16 centimeters. So this is the answer we have found. Okay, so we have solved the question. Okay, so we have solved question number 1A. We have solved question number 1E. So it has asked, for similar clay soil, how much settlement would occur at the end of 1 year? So after 1 year it will be 8 centimeter, and after 4 year it will be 16 centimeters. So this is the answer. Okay, now let's move to the next question. Okay, now question number 3. Okay, that means the third part, that is question number 1C. We have solved question 1A, 1B, and now 1C. So it says, what it is a theoretical question. It says, what is the efficiency, and explain different kinds of irrigation efficiencies. Okay, so let's see. So irrigation efficiency, so 5 irrigation efficiencies that you need to write. So first of all, conveyance efficiency, that is eta C. Then water application efficiency, that is eta A. Storage efficiency, that is eta S. And then water distribution efficiency, that is eta T, and eta U is the water use efficiency. Okay, now what is efficiency? It is the water available for use divided by quantity of water applied to the field during irrigation. Quantity water applied during irrigation. Okay, so it is the efficiency. Okay, now if it is of 5 types that you have seen. So efficiency is the water available for use divided by quantity of water applied to the irrigation field. Okay, now we will see different kinds of efficiencies. Okay, so first of all, see this diagram. This is very important. Okay, so if you remember this diagram, then it will be very easy for you to solve this question. Okay, so sometimes students get confused between which one is conveyance efficiency, which one is water application efficiency. Okay, so but if we remember this diagram, okay, then it will be very helpful to solve this question, because it is eta C, it is the WF by WD. Okay, so this by this. Now WS, eta A, that is application efficiency, WS by WF. Okay, so this, now what are these? So WD is the water delivered from the source. Okay, so it is water delivered from the source to the field. Okay, WF is the quantity of water that is diverted into the field, diverted into the field. And WD is the water from source, okay, from source. Okay, so eta C is the conveyance efficiency, and it is WF by WD, that is water, amount of water diverted into the irrigation field divided by total amount of water that has been supplied from the source. Okay, so this is conveyance efficiency, that is number 1. Now eta A, it is called the water application efficiency. Now the amount of water that is diverted into the field, not the entire amount is stored in the root zone. Okay, there is some loss. Okay, so in that case, suppose WS is the amount of water stored in the root zone, amount of water stored in the root zone. Okay, so it is the amount of water stored in the root zone. So in that case, eta A, that is water application efficiency, is the ratio of water stored in the root zone divided by water diverted into the irrigation field. Okay, so this is water application efficiency. Okay, the next one is the eta N. Okay, eta S, that is the, okay, so next one is the eta S. It is the water storage efficiency. What is that? It is WS by WN. Okay, what is WS? It is the water stored in the root zone. And what is WN? It is the amount of water that is required for to reach the field capacity. Okay, so suppose WA is the water available, that is moisture available. So WN is the amount of water required to reach the field capacity. So field capacity minus WA, that is the amount of water needed. Okay, so here you have first eta C, that is water conveyance efficiency. It is equal to WF by WD. So remember this diagram. Eta A, that is water application efficiency, that is water stored in the root zone divided by water diverted to the field, and then eta A storage efficiency is water stored in the root zone divided by water needed to reach the field capacity. Okay, so these are three main things. Okay, you need to write. Now two more efficiencies are there. So this is water distribution efficiency. Now what is that? 1 minus y bar by d. So d is the average depth of water. Okay, so suppose we take three depths, d1, d2, d3. Okay, so what is d? D is the average depth, that means d1 plus d2 plus d3 divided by 3. So this is the average. This is the D, average depth. Now what is y bar? It is the average deviation from the D. So if we take y1, then it will be equal to modulus of d1 minus d. Okay, so we will take the positive values only. That's why y1 is, y2 is equal to deviation from the mean for second depth, and y3 is equal to d3 minus d. Okay, so we have found three things: y1, y2, y1, y2 and y3. So y bar is the average deviation from d. Okay, so where y1 is equal to modulus of d1 minus d, y2 is equal to modulus of d2 minus d, and y3 is equal to modulus of d3 minus d. Okay, so y is the average deviation from d and d is the average depth. Okay, so what is eta d? Eta d is the distribution efficiency, that is equal to 1 minus y bar by d into 100%. Okay, so this is another very important one. Okay, now the next one is water use efficiency. Now it is the ratio of consumptive use of water by water delivered to the farm, that is water diverted to the field. So it is WF, as you know, water diverted to the field. And consumptive use, what is water consumptive use? Consumptive use means evapotranspiration. Consumptive use means evapotranspiration, that is evaporation plus transpiration. Okay, so the amount of water required is called consumptive use, consumptive requirement divided by water diverted to the field. Okay, so these are the efficiencies, irrigation efficiencies, that we need to write for the examination. Okay, so let's move to the next question. So we have solved this question, what is efficiency, and what are different kinds of irrigation efficiencies. Okay, now now the next question is, that is part number 4 of the question. It is question 1D. It's a question from transportation engineering. So speed of overtaking and overtaken vehicles are given as 70 km per hour and 40 km per hour in a two-way traffic road. Okay, two-way traffic road. The average acceleration is given 0.99 meter per second square. So we have to calculate the safe overtaking side distance and what is the minimum length of overtaking zone, and draw a neat sketch for overtaking zone and showing the position of the signpost. Okay, so it's a very good question, and I hope you have read the theory of this overtaking side distance. So let's solve the question. So first of all, what the question is saying, so VA, it is the velocity of the overtaking vehicle, that is 40 km per hour, 70 km per hour. VB is the velocity of the slowly moving vehicle, it is given 40 km per hour. A is the acceleration, it is given 0.99 meter per second square. T is the reaction time, we take it, we assume it as 2 seconds, the reaction time. L is the length of wheelbase, 6 meter, it's also we assume. Okay, then what is the OSD? Means overtaking side distance. Okay, and what will be OSD? What is OSD minimum and what is OSD desirable? Okay, so let's see. So first of all, step number 1, VA it is the velocity of the overtaking vehicle given as 70 km per hour. If we divide it by 3.6, we get 19.44 meter per second. Okay. Similarly, VB is the velocity of slowly moving vehicle, 40 km per hour. Again, divided by 3.6, we get its velocity in meter per second, that is 11.11 meter per second. Okay. Now, A acceleration of the overtaking vehicle is given 0.99 meter per second square. OSD was the overtaking side distance, and it is the sum of D1, D2, D3. Okay. Now, what are they? And we know D1, it is the distance traveled by A, that is overtaking vehicle, in the reaction time TR. Okay, and we assume that in this reaction time, this vehicle A moves with the velocity VB. Okay, if you have read the theory, you know why this assumption is made. And D2 is the distance traveled by A, that is overtaking vehicle, in the overtaking operation, during the overtaking operation. And D3 is the distance by C. C is the vehicle that is moving from the coming from the opposite side. Okay, C is the vehicle that is coming from the opposite direction, and we assume that its velocity is equal to the velocity of the overtaking vehicle, that is VA, that is 19.44 meter per second. Now, the main thing, so this we can say this is the overtaking vehicle. This is the overtaking vehicle, and this is the slowly moving vehicle. Slowly moving vehicle. So you can see it's a two-way road. Okay, two-way road, and here it is the overtaking operation. Okay, now see here, this is D1. D1 is the distance traveled by the overtaking vehicle in the reaction time. So it is in the reaction time TR. D2 is the velocity of the is the distance traveled by the overtaking vehicle during the time T, that is the overtaking operation, during overtaking operation. And D3 is the distance traveled by the vehicle C. So it is coming from opposite direction. This is this, and it is in the direction, and it is also in TO. So in the during the overtaking operation, what is the distance traveled by the vehicle C? So vehicle A, we assume its velocity VA, vehicle V is assumed VB, and vehicle C is assumed VC. It is equal to VA. Now let's move to the solution part. So step number 1 is gone. It's step number 2. D1 is the VB into TR, as we know. In the reaction time, we assume that the overtaking vehicle takes the velocity of the slowly moving vehicle. So VB into TR, as we know, VB is equal to 1.11 into TR, we assume 2 seconds the reaction time. So it is 22.22 meter. Step number 3, D2. D2 equal to 2S plus B. The equation for S is given 0.7 VB plus 6. You need to remember this. You need to remember this. Okay, so 0.7 VB is the velocity of slowly moving vehicle, that is 11.11 meter per second into 0.7 plus 6. So if we do this, we get value of CS is equal to 13.77. Now T is the time for overtaking operation. Time for overtaking operation to complete. So it is given as 4s root over 4s by A, where 4 is 4, and it is S is the 13.77 that we know from here, and A is given as the acceleration 0.99 meter per second square. So if we put these values, we get this. We get T is the overtaking duration of overtaking operation is 7.76 meter, 7.76 second. Now B. Now what is B? It is VB into T. Okay, so we know D2 equal to 2S plus B. So S we have determined. Now its value T. T is the overtaking time. VB is equal to 1.11 into 7.76. So VB is equal to 82.89 meter. Now D2 equal to 2S plus B. We put the value here, 2. S is equal to 13.77 meter and B is equal to 82.89. So if we put this value, we get D2 is equal to 110.43 meter. Now step number 4, D3. D3 is a distance traveled by the vehicle C that is coming from the opposite direction, and VA into T, we assume that it takes the velocity of the overtaking vehicle, that is 14, that is moving with 70 km per hour, that is 19.44 meter per second, into T is the overtaking time, that is 7.76 seconds. So if we put this, we get D3 equal to 145 meter. Okay, so D2 1110.43, D3 145, and D1 we have got. Okay, so D1 22.22, D1 22.22, D2 is 1110, and D3 is 145. So D1 22.22, 22.22, so, and D2 is 1110, 1110.43, and it is 145. So if we add these three, we get the value of OSD. Okay, so let's check what is the value coming. So OSD, step number 5, that is the overtaking side distance, it is equal to D1 plus D2 plus D3. So 22.22 plus 110.43 plus 145. So OSD, that is the overtaking side distance, is coming as 277.65 meters. So it is important, very important question. Now step 6, we know the minimum overtaking side distance. So this is for overtaking zone. For overtaking zone, uh, the minimum overtaking zone, it is the minimum OSD 3 into OSD. Minimum overtaking side distance should be 3 into OSD. It's coming 833 meter, and desirable overtaking side distance, that is a desirable length of overtaking zone, is 5 into OSD. So it is the minimum, it is a desirable, so it's coming 1388 meter. Okay, so this is the solution. And now here is a little bit of theory. So why overtaking side distance is provided? Overtaking side distance is provided for safe overtaking operation. Okay, so that its main purpose is uh, to fulfill the overtaking operation. Now why overtaking zone is provided? So overtaking zone is provided for overtaking, so intentionally provided. Now it is provided when it is not possible to provide the overtaking side distance throughout the length of the road. Okay, so it is so sometimes it is not possible to provide the overtaking side distance throughout the road. Okay, so in that case we use overtaking zone. Okay, so overtaking zone, but it is a particular zone marked with wide road for overtaking operation. Okay, so this is important, why overtaking zone is provided. Now we will see how signposts are given. So this is overtaking zone. So this length is 3 OSD, 3 OSD. It is minimum, it should be provided, or 5 of OSD. Okay, so write it here. It should be minimum 3 OSD, and a desirable is 5 OSD. Okay, now signpost. So here one signpost will be there. Okay, one signpost will be there. So this distance is, so you have to draw like this. This is overtaking side distance. Okay, now here one signpost will be there. This is overtaking side distance. Okay, one signpost will be there. So this distance will be overtaking side distance, and here another one will be here. This will be overtaking side distance. Okay, so this is the diagram. Okay, diagram. So this is the overtaking zone. So overtaking zone is intentionally provided. So here is one signpost, here is one signpost, here is one, and here is one. So this distance is OSD, this distance is OSD, this distance is OSD, and this distance is OSD, and this entire distance is 3 to 5 OSD. So this is overtaking zone. So this is the solution of the question. Okay, So we have solved the question A, question B, question C, question D. So total 60 marks we have solved. Okay. Uh, okay. So what we have solved so far. So question number 1A, that was the question from fluid mechanics, or from environmental engineering. Question number 1, we have used a Darcy-Weisbach equation. Question number 2A, question number, sorry, this is 1B. Question number 1B and 1C, 1D. Okay, so and question number 1B was from soil mechanics, and 1C was from irrigation engineering, that is efficiency irrigation engineering, and 1D is from transportation engineering or highway. Okay, highway or transportation. Okay, so total 60 marks, total 60 marks. We have solved total 60 marks in this video. Okay, so 60 marks, one question. So one question, it has 4 parts, each part 15 marks. So we have solved total 60 marks of the question. Okay, so this is the end of today's video. Okay, so I hope you have enjoyed this video, and if you find this video helpful, don't forget to share among your friends. Okay, so in the next video we will solve the question number 2. Okay, and then we will solve question number 3, 4 and 5 and so on. Okay, so these are the conventional type questions, so you need to practice these questions a lot so that you can perform better in the exam hall, because sometimes we think that we can solve it in the exam hall, but if you don't practice these questions, don't practice, if you don't practice this conventional type questions 2 or 3 times, then time management will be a big factor. Okay, so you will not be able to complete the questions. Okay, so let's end our discussion here, and in the next video we will again solve the questions in detail with explanation. So till then, stay safe, stay healthy, and have a nice day. Goodbye.